Okay, so far in this lecture, we've talked about finding inverses of matrices, and most recently, we talked about setting up matrix equations. So now we're to the point where we can use our inverse matrices to solve systems of linear equations that we have converted into a matrix equation. Okay. So we took our system of equations here, we have rewritten it as a matrix equation by writing out our coefficient matrix, our variable matrix, and our constant matrix. And last time, and as we'll see on the next slide, we found that we can isolate our variable matrix xy by multiplying both sides of the equation by the inverse matrix A inverse. Okay, so actually on slide 1, if you refer back to that, so let me quickly just write down what our matrix equation is. Okay, so our matrix equation is 2, 1, 5, 3. Our variable matrix xy, and our constant matrix 4, 6. Okay? And so if A is this 2, 1, 5, 3 matrix, if you refer back to the first slide, we did actually find the inverse matrix of this matrix already. And we found that it was 3, -1, -5, 2. Okay, so we want to solve this matrix equation using our inverse matrix, which means we're going to multiply both sides of our matrix equation on the left by A inverse. And you'll see why it's important that we multiply our A inverse on the left sides of the equation. Okay, so once again, we have our matrix equation. Okay. And we are multiplying on the left by our inverse matrix of A. Right? What we do to one side, we do to the other. Okay. So we know we need to multiply on the left so that when we multiply A inverse by A, we get the identity. And if you want an extra step here, really when we multiply a matrix by its inverse, we get our identity matrix, which is 1, 0, 0, 1 in the 2 by 2 case. Okay, and so remember, matrix multiplication is not commutative, so I couldn't multiply my inverse matrix on the right over here, or else we would get a different matrix. And in this case, we couldn't multiply because the rows and columns don't match. Okay, and so then all we have to do is multiply these matrices here. Okay, so we've learned our matrix multiplication. So first of all, we check. We have a 2 by 2 matrix and a 2 by 1 matrix. Since the columns in the first matrix equals the rows in the second matrix, we can indeed multiply the matrices. Okay. And the dimension of our new matrix will be a 2 by 1. So in our first row, first column, we take the first row of our first matrix and multiply it by the first column of our second matrix. So we get 3 times 4 plus -1 times 6. And for our second row, first column, we get -5 times 4 plus 2 times 6. Okay. Okay. So then, if you wanted to go through and check that this is indeed just xy, because we're multiplying by the identity matrix, you can. But on the left, we do just end up with the matrix xy. Okay. And doing the arithmetic here, we get for our first row 6 and our second row -8. Which means that x is equal to 6 and and y is equal to -8. Or you could write it as the coordinate pair 6, -8. And that is our solution. Okay. So for the next slide, we're going to use matrix inverses to solve the following system of equations. Okay. Well, the first thing we need to do is we need to write this system as the system of linear equations as a matrix equation. So first we need our coefficient matrix. Our coefficient matrix is 1, -1, 0, just 0. Okay, for our second line we get 1, 0, -1. And for our third line we get 6, -2, -3. And that's our coefficient matrix. And then our variable matrix in this case, we have 3 variables, x, y, z, and it is equal to our constant matrix, 2, 3, 15. Okay, and on the exam, when I ask you this question, I will give you the inverse of the coefficient matrix, so I will tell you that A inverse is equal to -2, -3, 1, -3, -3, 1, -2, -4, 1. Okay, we've already done an example of solving for a 3x3 matrix inverse using row operations and augmenting the matrix with the identity, so I won't do that again. But again, on the exam, I will, when I ask you for a 3x3 matrix inverse problem, I will just give you the inverse matrix of the coefficient matrix. Okay, so to solve our system, to isolate our variable matrix, we'll need to multiply both sides of the equation on the left by our inverse matrix. Okay, so we have A inverse times, let me just call this A, x, y, z. I don't want to write out that matrix. -2, -3, 1, -3, -3, 1, -2, -4, 1, and 2, 3, 5. Okay. So I mean, this step isn't really necessary. I just want you to see that our A inverse and our A are indeed inverses of each other. So we'll just get the identity, and ultimately on the left, we are just left with our variable matrix. Okay, so now once again, all we have to do is multiply two matrices. Let's check their dimensions. So we have a 3x3 matrix and a 3x1 matrix. The columns in the first matrix equals the rows in the second matrix. And the dimension of our new matrix will be a 3x1. Okay. So for our first row, first column, we're taking the first row of our first matrix, multiplying it onto the first column of our second matrix. So we get -2 times 2 plus -3 times 3 plus 1 times 5. For our second row, first column, multiplying our second row onto our first column, we get -3 times 2 plus -3 times 3 plus 1 times 5. And for our third row, first column, we get -2 times 2 plus -4 times 3 plus 1 times 5. Okay, so simplifying, we get x, y, z is equal to, so for our first row adds up to 0, our second row adds up, 2, our second row adds to 0, and our third row adds to -1. Okay, So that means our solution, you can either write out that x is equal to 2, y is equal to 0, and z is equal to -1, or you can write it as the point in 3D space 2, 0, -1. Okay, so there is our solution. Okay, so really all this comes down to is just matrix multiplication. And again, remember we're multiplying on the left. Okay, so finally, our last example, use matrix inverses to solve the following systems of equations. So once again, if we're going to use matrix inverses, we need to rewrite this system of equations as a matrix equation. Okay, so our coefficient matrix is 2, -3, -4, 6. Our variable matrix is x, y. Okay, and our constant matrix is 8, -5. Okay, again, remember we need to solve this, so we'll multiply both sides on the left by the inverse matrix of our coefficient matrix, which we can find this one, so let our coefficient matrix, let's call it A. Okay, then A inverse is equal to, we can use our formula that we derived. Okay, so maybe let me just write it in the corner. Again, if we have a matrix, 2 by 2 matrix A, B, C, D, then our inverse matrix is 1 over AD minus BC. Multiplied by, we swap our D and our A, and we negate our B and our C. Okay? Okay, so we get A inverse in this case is 1 over 2 times 6 minus -3 times -4 multiplied by 6, 3, 4, 2. Okay, and what happens? Well, here in our denominator, we get a 1 over 0, which means, okay, so here we're dividing by 0, which means that A inverse does not exist. Because if you remember, if the determinant AD minus BC equals 0, then there is no inverse. Which means that there's no solutions for this system of equations. So, no solutions. Okay, so that's all the material that will be on Chapter 6.